Our next session is with Volker Krummel, Head of Technical Research at Utimaco. Volker will be sharing valuable insights on navigating the PQC migration challenges, especially when deploying stateful hash-based signatures in HSMs. He'll explain how these advanced algorithms are shaping the future of cryptographic security. Volker will also present a framework for secure deployment in distributed systems, making the PQC transition smoother for everyone. Let's welcome Volker.
Yeah, hello everybody. Welcome to my talk, Overcoming PQC Migration Challenges. My name is Volker Krummel. I'm from Utimaco, and they are responsible for all of the topics regarding post-quantum cryptography and migration to the post-quantum era. What is the talk about? We have three different main topics here. First, introduction. A brief introduction, who's Utimaco, what is done with PQC. Second, what are the market drivers in PQC that we see so far. Third, the quantum threat, how can you address it and stay secure, even in the advent of quantum computer and quantum attacks. And the fourth is a bit more technical topic about stateful hash-based signatures. They provide a lot of benefits, also get some challenges with these, and we would like to present our framework to a proper state handling to mitigate most of these challenges in context of stateful signatures. So, Utimaco and PQC shaping the future of cryptography. Utimaco is one of the market-leading providers of cryptographically based IT security solutions and services. Three main fields, let's say, we can subsummarize here is data protection, key management, or management of cryptographic keys, and secure payments. Data protection, so you can protect your data files, whatever. Having a GP, HSM, and a hardware security module that provides a secure home for your cryptographic keys and the sensitive cryptographic execution of cryptographic algorithms. According to that key management, you have to manage your keys, your cryptographic keys in a very secure and efficient manner. And lastly, secure payments for financial industry, market leader in payment HSMs and providing secure payment services all over the world. We provide these as on-premise solutions / products, but also most of them as a service for cloud environments and the same. So what is the PQC challenge and why is Utimaco, how is Utimaco addressing the new changes and the new threats that are coming up with in the context of quantum computing and post-quantum cryptography? So Utimaco is very active in staying ahead of the curve, of the technology curve, collaborating with a lot of agencies, collaborating firstly, of course, with NIST. This is the very important collaboration because NIST is driving the PQC algorithm challenge. You may have heard of, it's let's say the most important selection process in the world for PQC algorithms. But there are also many other agencies and organizations around, for example, European ETSI, the German BSI, Bundesamt für Sicherheit in der Informationstechnik, and application domain-driven organizations like X9, GSMA, the PKI consortium, ENISA, and so forth. This is very important work to stay ahead of the technology curve and to be part of the new developments. And we were recognized in 2024 2 times invited to the White House PQC roundtables. So it's really an important play field for us to stay knowledgeable and distribute our experience into the market. We were recognized by Frost & Sullivan to have the best, let's say, PQC strategy in the field of HSMs. We have dedicated leading customers. The biggest companies in the world are our customers that already use PQC in the field in an operative environment. We file our own IP in the context of PQC, not with the algorithms itself, but with the surroundings. So with, for example, the state handling and the management of PQC and stateful hash-based signatures, and also for the migration part. And a very important part for us is also to stay interoperable, so that there's no, let's say, vendor lock-in. If you choose one of these vendors, it's the interoperability that we already proved in the past, and we continue to prove it for our current and future products. So what are the market drivers for the PQC, so the post-quantum cryptography? We identify, let's say, 2/3 different driving leading drives. The first and the most important for us is, of course, the CNSA 2.0. This is a requirement document for the US government and US government-related business, stating that the transition to PQC is really an urgent and very important topic for all of the governmental environment. A lot of European governments align with these recommendations and requirements, and we will see on the next slide that the timelines that are given in this document are really demanding and underline the urgency for the US government and the European governments. Since August this year, we have the first 3 winners of the NIST PQC competition as final standards. The ML-DSA, ML-Chem, and SLH-DSA, 2 signature algorithms and 1 encryption algorithm is already standardized. Not to forget that stateful hash-based signatures, exactly the class of signatures we will talk later a bit about, were already standardized in 2020. So we have, let's say, a variety of possible selections for signature, post-quantum signatures. The last part here, as I said before, the standardization and interoperability tests are very important to us so that we can prove and show to our customers and to the market that our products are interoperable with the competitors' products. For example, verifying a signature on our HSM that was generated by a competitor's HSM must be possible. And this is a very important part for us to stay compatible here and to provide the best interoperability. The CNSA 2.0, as I said before, states certain requirements for dedicated use cases. That means for dedicated use cases, there are a selection or sub-selection of PQC algorithms recommended or required. But there's also a timeline, a very tough timeline that you can see on this slide for selected use cases. For example, for the software and firmware signing use cases you have in your environments, the NSA requires from 25 on, so from the beginning of next year, that you do the transition to PQC. Fully, and you have, let's say, time to the year 2030 to conclude the transition, because after the 2030, no non-PQC solution for software and firmware signing will be accepted anymore. That does not mean that you can wait until 2030, because, of course, competitors will jump onto that migration maybe earlier, so you really have to make up your mind and to have a good strategy for your software and firmware signing use case. The same with web browsers and servers for cloud services. A bit more time is given for traditional network equipment, operating systems, and certain other use cases. but we will see that there will be a tremendous speed up since now we have the final standards from the NIST process. The migrational, let's say, activities are increasing tremendously. So these are the market drivers. What's about the quantum threat? So the quantum threat, I think everybody is aware of. If a cryptographically relevant quantum computer will exist, it will be able to break all the asymmetric algorithms, cryptographic algorithms that we use so far in the field, especially RSA and elliptic curve encryption and also signatures. This, of course, causes a great threat to data and to services that we use in the field today and that are protected by cryptography today. There are some subtleties in these threats because it's not clear that you can wait until such a quantum computer really exists. But for example, the confidentiality of data that is encrypted today is already at risk because you can store the encrypted data today and wait for the advent of the quantum computer and then decrypt it at that time. And depending on the severity and the sensitivity of the data, this may still cause problems even if the quantum computer is there only in 10 years or maybe 12 or 15 years, depends on your data, on the confidentiality requirements of your data. A bit different, the situation for the signatures, but even here, as soon as the quantum computer is there, it will break all the security of the signature algorithms we use so far, which may result in impersonation attacks if you are from the viewpoint of a human. But also we have a lot of use cases on the IT in the IT sector. For example, secure firmware updates. A firmware update is typically secured. It's signed by the vendor and verified by the device before installing it. And of course, you can imagine if a quantum computer can break this signature, then you can manipulate firmware and cause a lot of problems for virtually all IoT devices, industrial devices, and mobile phones and cars and everything that's out in the field. So it's an important and very important and dedicated threat to the whole IT infrastructure. Our position, the position of Utimaco and most of the specialists and experts in the field, is of course to recommend a holistic approach to address this threat. Meaning, it's not only about changing an algorithm here and there, but you need firstly to have, let's say, a good overview and a good picture about your complete system and especially to all of your use cases. So the heading crypto discovery and control reflects this in the sense you need to know which type of crypto you're using currently. This is the first step, and the second is, of course, keep the control over the crypto that you're using, especially for the algorithms that are selected, the key management for the cryptographic keys you use, and things like that. That does not mean that you have to do some kind of inventory first for your whole company and then start doing some actions and decisions. But our recommendation is doing it use case by use case. Typically, new use cases, new products, new projects start in the upcoming future. And of course, it would be wisely to think about and to address the quantum threat directly in the new use cases. And of course, doing the control and the crypto discovery for the existing use cases that helps you in out a migration plan, how to migrate old and existing use cases to the PQC world. The second pillar is go for standardization. So go for standardized algorithms. Try to avoid as much as you can proprietary solutions for your use cases. This is, of course, supported by the industry and by NIST especially in standardizing cryptographic algorithms, but it goes much further. For example, APIs, interfaces to libraries, to hardware security modules, and things like that. So stay as close to the standard as possible, because we know from the past, proprietary solutions provide a lot of challenges and a lot of computational and financial overhead in the future. A good architecture, a good security architecture involving cryptography also should consider and involve hardware security modules, so a safe and secure home for your cryptographic keys and your the execution of sensitive cryptographic algorithms, for example, like signing processes and stuff. You can save a lot of trouble and a lot of challenges if you go for certified and very secure environments for the cryptography. And last but not least, distributed environments. Typically, use cases are not monolithic in the sense of that you have a single instance where you run the cryptography, but you need to distribute it either for business continuity or because of the location, different locations that are part of your use case. You should also consider this in your, let's say, new architecture for the quantum, to address the quantum threat. Saying this, I would like to switch over to a dedicated class of signature algorithms that are secure, provably secure against quantum computers. They are the so-called stateful hash-based signatures. I will explain the name, the more or less complicated name a bit, and drive you through the challenges and a solution that addresses most of the challenges of these algorithms and make them really a good choice for use cases where, especially where you use or need long-term security. So the stateful hash-based signatures, they have pros and cons, as I said before. For example, they provide at the moment the best ratio of public key size and signature sizes. It's really a very efficient way to establish digital signatures. They are very mature. The basic design dates back to the 1970s. It's well understood. It's the security guarantees and the security requirements are well understood. And let's say cryptography community regards this as the most mature type of algorithm for signatures. As I said before, they were already standardized, so by NIST, so they are already there and ready to be used and implemented. Even agencies and organizations that do not fully trust new signature or PQC algorithms, therefore recommend going hybrid first in the first transition phase, meaning combining the new algorithms with the old algorithms to thwart maybe implementational attacks or weaknesses. Even these organizations regard the stateful hash-based signatures as a one-to-one substitution, so that you are able to jump over this hybrid phase and go directly to a single signature scenario. The drawback, or let's say challenges of these algorithms, are that they are stateful. I will go a bit and explain what stateful means. Briefly saying, stateful means you need to know your current status of your algorithm, of your key, because you typically the overall key consists of a set of so-called one-time signature keys. One-time signature keys means you should only use one of these keys at a time, and do not reuse these OTS keys. And so you need some type of bookkeeping about your set of OTS keys, and this is exactly what the statefulness of these algorithms is. Since you have this bookkeeping, you can directly think of these algorithms provide or give some challenges for distributed setups, because you need some kind of alignment between the different sites. And therefore, it resides also challenges for supply chain scenarios where you have different entities along the supply chain that uses the same signature mechanism for authenticity, for example, for firmware upgrades and stuff like that. For the stateless algorithms that we use today, these are more or less solved. You can just distribute keys without thinking about this. The stateful ones require a bit more thinking, but as I will show you in the later slides, we can mitigate most of these challenges within our framework. So we already have experiences with concrete implementations, concrete use cases in certain application domains. For example, for the automotive industry, the use case of firmware signing for cars, or at least for parts of the cars, is a challenge to the cryptography, because not only of the distribution, but also of a long lifetime for components and cars in the field, so more than 15, 20 years typically. So you really need a mechanism that is really reliable, and for these type of use cases, you typically choose the most mature algorithms that you can find. So the stateful hash-based signatures are a good option for these use cases. Here you can see that simply signing a firmware for a component of a car also reflects some kind of infrastructure behind, some kind of PKI solutions, HSMs involved, setting up and providing a full infrastructure to supply the development process and production process with cryptographic signatures. And of course, all of these steps here and all of these components have to be post-quantum cryptography related, because as you know, in the security field or in the cryptography field, the weakest link provides the level of security. If you have a weak link in your overall system, then the attacker will find this and exploit that. So you have to have a holistic security level of overall of your use case scenarios. When you look a bit deeper into these, for example, firmware signing scenarios for automotive and for maybe also satellite communication and things like that, you see that in the easier way, on the left side, you have a centralized use case where a central unit can distribute keys or can distribute signatures, which makes the life a bit easier with respect to the overall setting. But typically in industrial settings, you have scenarios like a bit more like on the right side, so decentralized. So you have production sites, units distributed all over the world that have to be aligned on the cryptographic level. And exactly here, we will face the challenge of the stateful hash-based signatures, and we will show how to solve this. Now comes a bit of a technical slide that you may skip while listening to this talk, just to give you an idea how the stateful hash-based signatures work, so that you can understand the challenge from a technical level. So having a cryptographic hash function called H in this diagram here, we built up a so-called hash chain starting with a random value x0, and then hashing this value, getting x1, hashing this x1, getting x2, and so forth. And exactly this is the basis of the signature algorithm, because we can see all of the values but the last as a private key and part of the private key, and the last one we regard as the public key. Since we have a cryptographic hash function here, which has certain properties, one important property is that you cannot go backwards. So knowing x3 does not help you in computing information about x2 or even other x values here. So for example, if you want to sign a message 1, it's a very, very primitive and simple process. You select the according index of the random values, the x1, and x1 is the signature of 1 for this key. The verifier, on the other hand, knows the message 1 and the signature 1, and knows the public key x3, and can do the verification quite easily because he knows the text, the 1. He knows how many steps he had to do and to reach the public key. So he can start and enter the chain from above at the value x1, and then do the hashing, because this is a non-keyed function, can do the hashing and see if after 2 iterations reaches the public value x3 or not. If it reaches x3, then the signature is verification was successful. If it does not reach, then the signature verification was unsuccessful. So this is the basic concept. What you can directly see, okay, you should only do this and use this key combination only once, because if I, for certain reasons, why I know the x1, then I can compute x2 and could forge an x2 message afterwards. There are some other technical subtleties here in this, but this is the basic concept. So having an OTS and one-time signature scheme like this is the basis, which is not very efficient for industrial or real-life applications, because what you need is, of course, the ability to sign more than one message. And what you need is a common public key that you can embed into your firmware for signature verification. And there's a smart way to combine a lot of these OTS signatures together, simply by joining the public keys of all these independent OTS signature schemes, in the sense that you combine 2 of them via a hash function, and then you combine 2 of the intermediate results by a hash function, and then you combine and combine. So you build up a tree which results in the root node, and the root node is the common public key for all of these OTS schemes. And then you have the efficiency that you have a single public key that you can embed in your device, and you can use this one to verify all of these OTS keys, all of these OTS signatures in the field when they show up. For example, if you use OTS 0 and 1, since they have this OTS requirement, you have to discard them. And this is exactly what I mentioned before. this is exactly the state handling. So you have to remember to not reuse these keys. If you, for example, now use OTS2 as a signature scheme, you provide the verifier not only with this OTS2 signature, but you give some intermediate values that are marked here in yellow. And these intermediate values allows the verifier to recompute dedicated intermediate values of the tree and climb up the tree until to the public key. So in the first step, it will compute from OTS2 and OTS3 public key the green value here, and then combines the green with the yellow on that level, and then on that level, and finally reaches up to the public key. So as you see here, the verification process is more or less the same as with a hash chain, but it allows you to have a tremendous number of OTS signature schemes combined with a single public key, which makes it very, very efficient. But as I mentioned before, challenges remain. You need to keep track. You need to keep track of the state of the number or of the OTS keys that were already used. And you have a limited number of signatures, which can be arbitrarily large and large enough for virtually all use cases. But it's limited in the sense that you have to decide before setting up the whole signature system. So the main problem, if you are, let's say, some kind of operator, IT operator, a big challenge that's directly comes to your mind is the backup and restore. For example, as in the picture before, you have this OTS 0 and 27 stored in an HSM or in some key management system. You take a backup. This is a good practice, of course, backing up as soon as possible for general IT services. Then during the operating phase, you use some of these keys, for example, OTS 0, 1, and 2. So you're fine with it. And later in time, you restore your backup that you took in the beginning. And of course, exactly at that position, you lose the state information. So you lose the information that you already used, OTS 0, 1, and 2. So your system has to ensure that this must not happen, because if you reuse one of these keys, you lose the security of your signature scheme. Another challenge is, of course, if you have a distributed environment. You have several, for example, manufacturing sites. You have a supplier site, maybe for contractor. You have some kind of headquarter. And now you can imagine if you want to have an aligned view on the state, it's really challenging. And if you think a bit deeper about this, it's not only about database synchronization or things like that. These are not secure enough for the cryptographic from the cryptographic viewpoint. So you need a different system that is more thorough and guarantees that you cannot reuse OTS keys, maybe by race conditions or by user failure or stuff like that. So to address this challenge, we present a framework here, a so-called OTS-preserving framework. So one-time signature preserving framework that consists of 3 different ingredients. So first, we have a trust relationship between HSMs. This is more or less standard for HSMs. This is not a big thing. We have our new, let's say, OTS-preserving communication between these HSMs in that trust relationship. And we can boil down the global state management then to a local state management, which is more or less straightforward. How this works, I will explain later in a brief animation how this works. But these are the ingredients that we need for our preserving framework. If you use that framework, you are sure that you will maintain the OTS property of your system, and you can use the stateful hash-based signatures without the danger of losing the security here. The HSMs are still passive, so we do not change the role of HSMs in that context. The logic that is not the security relevant is still driven by the application or by a software layer that is triggered by the application. So, design principles, these are more or less technical design principles that are important firstly for the security, but also for the business continuity, the availability, and the operating. Our design concept was also security is not an option. Yeah, it's mandatory in this, but it has to be usable for the operators and not increase the complexity of the operating too much. So let me go through briefly through some of these points so that you can really see what's going on. If you have any questions, I think there's time to ask questions, or you can reach out to me and we will discuss this in more depth. So security view, a comprehensive security design. This reflects from our position that all of the security relevant processes, mechanisms, algorithms, and things like that should be inside of an HSM. This prevents, of course, attacks, inside attacks, and misbehavior or misusage of certain things. So this is a mandatory, let's say, property for us. Separating key information and state information, that gives us a lot of flexibility here and increases the security even further. Authentic and confidential end-to-end transfer. This is clear, let's say, from a security perspective. But since we are dealing here with a very, let's say, mature class of algorithms, we also need a very mature level of protection of the state handling framework. And for this, we went back and designed our framework entirely based on symmetric encryption, which is as mature as the stateful hash-based signatures that we are protecting. We have this trust relationship between HSMs, which gives us a lot of security and flexibility. I will show this on the next slide, what the flexibility will look like. And of course, things like replay attacks, since we are in a communication in protocol layer here, we need to prevent replays and to protect the freshness of each message to ensure the OTS property. On the operator side, there are certain concerns since we have only a limited number of keys. Due to misbehavior, for example, there could be an exhaustion of keys. We address this, that you can also store parts of the state and the keys offline outside of an HSM, so without a reach of any application. We do not need any communication, any direct communication between HSMs during the operating. The transfer of messages can be done via network, but also can be done via file transfer, USB stick, air-gapped for air-gapped environments and things like that. We do not have a static setup, so you can start small with a small number of nodes slash HSMs, which you can enhance in the future, or you can reconfigure these and reconfigure the whole setup even during the operating phase. So there's no, let's say, basic decision in the beginning that will limit your use case in the future. No master slave, so all of these HSMs, all of these nodes are more or less the same. And the method that we provide, the framework, is generic, so you are not limited to a dedicated subset of these cryptographic signature algorithms, but you can use it for all of these. So let me show you a very, very basic picture to show you how simple this system works. Assume that you have 3 sites where you want to use parts of this tree key that I showed you before. So we have installed HSMs on each of these sites. We have some kind of logical connection. As I said before, we do not need direct connection, direct communication during the operating phase. This could reflect the network, could be portable storage, whatever. And we have an option here to as external key storage. I will show you how we use this. This is a let's say, security relevant component that is able to store data like a generic database. And since our concept puts all of the security relevant stuff inside of HSMs, we are free to store secured data and secured messages inside of an unsecure database. So let's start. So assume you want to go productive. You have a setup phase where you set up the trust relationship between HSMs, meaning we create a trust boundary around these HSMs by generating a symmetric key inside of the HSMs that allows the HSMs to authenticate and to communicate confidentially. We have this as in the picture. You see the red dashed line, which is a sign of a trust boundary around this. So inside of this boundary, everything is secure. Outside, everything is not secure. Not to mix this up, so the HSMs 1, 2, and 3 are part of this. All the rest is not part of the trust relationship, and do not be protected in a certain manner. Now, in this very basic scenario, you generate OTS keys in HSM1. You can also distribute the generation of these keys directly and start with a portion in HSM1, 2, or 3. But for the simplicity, we start with this basic scenario. So now you have these keys inside of the HSM, and you want to distribute them because you want to make them usable in manufacturing site A and B. So you transfer parts of the keys from the headquarters, from the HSM1 to manufacturing site. Here in the picture, you just directly transfer it to some storage, and then you incorporate only one of these keys into the HSM. So this key is usable now for generating a signature. And the OTS 5 and 6 are not yet usable and may not be fell prey to an exhaustion by mistake, for example. You can distribute further keys to HSM3, so you have the full flexibility of transferring keys back and forth from one HSM to another. This is, let's say, the security guarantees rely on our communication, OTS-preserving communication protocol here, so that you are free in distributing using that protocol, and the HSM protects you from doing any misbehavior. So the protocol is hosted inside of the HSM. And therefore provides the maximum level of security. If you're now in the operating phase, as I said, you have the maximum flexibility. You can change the number of HSMs inside of this trust boundary. So, for example, you could discard HSM3, before discarding, retransferring the keys back to another HSM, maybe HSM1 or HSM2, so that you do not lose keys. You can also add further HSMs to the trust boundary and transfer keys to the new HSMs. Of course, attacks are blocked by the security design of the protocol. You can store keys offline, and if ever an HSM really is destroyed, stolen, gets lost, whatever, you only lose a very limited number of well-defined keys. So you still know what you lost and what is still available. So this makes the stateful hash-based signatures really usable in most of the reality scenarios. As I said, yeah, you can add and remove HSMs from the trust relationship, so you're much maximum flexible with your architecture and your setup. You combine all this with the monitoring, of course, so that you know which key is stored in which HSM, what's going on, and also triggering, of course, the sending and receiving of messages and keys. So this monitoring / control center gives you maximum of control about the overall, the worldwide use case and the status of this one. So this combination really addresses most of the challenges, and we see in the field that customers really adopt this and use this in productive environments. So summing up, stateful hash-based signatures are or provide or give you some challenges on the first side. With a proper holistic approach and a proper state handling framework, we can address most of these challenges and make these very, very mature signature algorithms really usable for industry execution and industry use cases. What you need for this is, of course, HSMs. So you need a hardware security module, maybe from Utimaco, maybe from a competitor. With the Utimaco HSM, you get the hardware protection, you get flexible firmware concepts so that you can load PQC extensions. So the new algorithms are provided as firmware extensions. You can load them onto the device and then make them usable in a very high security environment. We also provide an SDK so that you can write, in principle, your own firmware modules if needed, if there are any complex situations. So you can run your code inside of this secure environment. We provide a fully functional simulator, so pure software simulator of the hardware security module. This simulator, of course, does not provide any hardware security, but lets you do some testing, some integrational, some implementational work against a very flexible software simulation environment. And of course, we round up this offering with an HSM management and monitoring solution so that you really know what's going on your HSM fleet and are always up to date. And with this slide, I will thank you for your attention and be happy to take questions. Thank you very much.
That was a really informative session by Volker. Unfortunately, he couldn't join us live for the Q&A today, but if you have any questions for him, please email your questions to us at info@encryptionconsulting.com and we'll make sure he receives them. We've got 2 more sessions lined up for you, so stay tuned.